Hi there. This is Space Nuts, a Q&A edition. My name is Andrew Dunkley, your host. Great to have your company. Hope you're well. Coming up on this episode, Fred will be answering questions about angular momentum, the age of the universe versus the perception of time. That's an interesting one. The vastness of space and the big leap. Stick around. We'll deal with all of that coming up soon on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2,
3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And we welcome him back once more. It's Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew.
How you doing?
Seeing you here.
Yeah,
Doing
it's
fine,
so
thank you.
unusual.
Doing all right.
Seems like ages since we last spoke.
Yes.
Could have been a few seconds, though. Who knows? We'll be talking about time shortly, so maybe the answer is in there. Let's get down to business. This first question comes from Mark. Now, it's actually two questions about angular momentum, but Mark, he's sort of weeding this one out a little bit. So let's find out what he wants to know.
Hello, fellas. My name is Mark, and I reside in Baton Rouge, Louisiana. My first question, has to do with the two black holes that were very rapidly orbiting each other just before they merged. And each of those black holes presumably had its own angular momentum and was spinning in a certain sense, either clockwise or counterclockwise. And my question is, if these two black holes, as unlikely as it might be, happened to be spinning with equal rates, but in opposite directions, in such a way that the net angular momentum of the combined system would be zero, then would the final new black hole created have an angular momentum of zero? I'm not sure if I posed that correctly, but I'm sure you get what I'm meaning here. Could the resulting black hole have a net angular momentum of zero? And if so, would that result in any unusual characteristics if a black hole was not spinning? Anyhow, that's my first question. My second question has to do with the universe writ large. Wouldn't the universe have a net angular momentum? When the Big Bang occurred, I presume, although I don't understand why there would be a non-zero angular momentum of the entire universe. If the Big Bang was perfectly symmetric, the net angular momentum should be zero, should it not? And of course, the Big Bang was not perfectly symmetric, and that is what I understand is the reason for the clumping of matter as shown in the WMAP image. I guess I'm getting too off the beaten path here, but anyhow, it has to. My question is: does the universe have a net angular momentum, and what's the implications of that either way, whether it does or does not? Anyhow, see, that's why I stay awake at night. Okay, guys, love your podcast. Take care.
Thank you, Mark. Yeah, there's a lot packed into those ideas from Mark. Fred, double barrel question. We'll start off with the two black holes merging with equal rates in opposite directions. Would they achieve zero angular momentum under those special circumstances?
And the answer is yes, they could. So there are two things at play here. One is the individual spin of each black hole, most black holes are spinning. And so those two, the angular momentum of those two, of each black hole, when they collide, it could be that they'll cancel out if they're rotating at the same rate in the opposite direction. Now, normally, that's unlikely to happen because it would be very, very unusual to have two black holes with exactly the same rotation rate, but one the negative of the other, one rotating in the opposite direction. But it could happen. It could happen. But the bigger phenomenon is actually the orbital angular momentum of the two black holes as they spin together. That's where most of the angular momentum in a binary black hole, a pair of black holes, that's where most of it lies. When they collide, what happens to that angular momentum? Well, it is radiated away in gravitational waves. And that's one of the things that is taken into account when people look at a gravitational wave signal coming from two colliding black holes. The angular momentum gives rise to the change in angular momentum is one of the things that gives rise to the gravitational waves that are observed, and that's all modelled and all makes complete sense. So in particular, though, that means that that's the biggest component of spin. The individual spin of each black holes is a smaller one, but still, it basically is exactly as Mark has postulated. They could cancel out completely. What happens to the angular momentum? Once again, it is radiated out in the form of gravitational waves. So that's where the angular momentum goes. It's a form of energy, and that comes out as energy that we can now measure with our gravitational wave detectors. And turning to part two, which I think is...
Yes, the universe. Assuming that it radiated out in all directions simultaneously in a spherical way, would it have and should it not have net zero angular momentum?
And apparently it does, the sense that it has never... There's no evidence for a rotation of the universe as a whole. Mark, again, is on absolutely the right track, because if there was a rotation in the universe, you'd expect to see particular patterns within the cosmic microwave background radiation, which is what he mentioned in relation to WMAP, the Wilkinson Microwave Anisotropy Probe. And we don't see that. We don't see characteristics that would suggest that the universe is rotating. So it looks as though there was enough symmetry in the Big Bang itself that no rotation was imparted to the universe. And one of the other issues with this, of course, is if it was rotating, then you have to basically invoke a central point and an absolute reference frame, and neither of these things are permitted in our normal cosmological theories. So it's just as well that it's not there. And it's the fact that we don't see any rotation that allows us to ignore, the idea of an absolute reference frame. We just take the universe as a whole.
It's like a snow globe. Like the snow globe's got no angular momentum, but everything inside's doing all sorts of busy stuff.
Yes, that's right. That's a very nice way to put it. You'll go far, Andrew, with analogues like that.
I went to a tourist shop to figure that out. Yeah.
You've got to choose the right snow globe.
That's right. Did you know that people who invented snow globes never, ever, to this day, it's still a trade secret, revealed what the glittery stuff inside a snow globe is?
No, I didn't know that.
It's true. No. Look it up. The original inventors and the family that started it still has control of the invention to this day. Have never ever revealed what is inside a snow globe, what makes all the glittery snow-like effect. They've never told anybody. I think it's the same stuff they put on KFC nuggets. But I could be wrong. I could be wrong. Secret herbs and spices, maybe. Thank you, Mark. A very thoughtful question, and it sounds like you were on the money, so you can actually go to sleep tonight. Well done. Our next question, Fred, comes from John. Does the age of the universe depend on the gravity well that you exist within? If Andrew was living on a planet orbiting a supermassive black hole, e.g. Sagittarius A star, time would be slower for him relative to Fred living on Earth. Would Andrew then calculate the age of the universe to be less than what Fred does? That one comes from John. That's a good one. That's a what-if question.
It is. We should try it out one day, Andrew.
Yeah.
You can be the one going and living on the black hole.
Yeah, I don't think it'd be a very long-lived situation, but, I'm happy to give it a whirl.
So, turning to the answer to John's conundrum, the answer is yes, there is gravitational time dilation. So if you were hanging around a black hole, you'd think the universe would have a younger age than an observer in deep empty space. But it is a small effect compared with the size of the universe at large. So what we do is we treat the age of the universe as a universal constant. And you can sort of imagine when we look at, for example, the cosmic microwave background radiation, we look around the whole sky and we see the flash of the Big Bang, and we assume that it's the same age in all directions. And that's basically what we do. We take the flash of the Big Bang as being our yardstick for the 13.8 billion years age of the universe. And that's, so it irons out, if I can put it that way. This is the global view that irons out all the local funny gravitational effects, like you hanging around a black hole and seeing a younger universe. This is the what you might call a measurement made in a preferred reference frame. You're just talking about reference frames in terms of a rotating universe. This is the same issue. This is the sort of standard reference frame of the universe, kind of defined by the cosmic microwave background radiation. And so gravitational effects on that whole picture are minimal compared with what might be felt when you were very close to something with a very high gravity.
Okay. All right. I was surprised that it went the way you said, because I thought you were going to say, no, for me, time will pass as it would anywhere else. It's just, to the observer, it would be different. You wouldn't be moving. But no, from the inside, it would be different, because what you're looking at on the outside would age slower, therefore seem younger. Is that what you said?
Yes, that's right.
Yeah.
So the it is. It's you're observing from a different reference frame when you're hanging around the black hole, it's. I mean, we normally think we talk about people falling into a black hole and time stops on the event horizon as they cross the event horizon. But that's how we normally think about these things. But if you yourself are in the black hole, then it looks as though the whole universe is doing different things, like becoming younger and things of that sort.
Extraordinary. Yeah. It's just such a weird place, isn't it? When you're
very weird, yes.
All right, John, great question. And the answer was yes. This is Space Nuts with Andrew Dunkley and Professor Fred Watson, a Q&A edition. Let's take a short break from the show to tell you about our sponsor, NordVPN, and to discuss your online privacy. Because let's face it, these days, whether you're browsing at home or jumping onto public Wi-Fi at a cafe or an airport or wherever, your data is constantly at risk. Hackers, trackers, even companies you've never heard of, they're all trying to get a piece of your digital life. And that's where NordVPN comes in. Our sponsor is fantastic. It's one I've been using for many years now myself, and I have absolute faith in their product. NordVPN encrypts your internet connection, hides your IP address, and keeps your personal information safe from prying eyes. It's like putting an entire online world inside a secure tunnel. They've got over 7,700 servers worldwide. You can browse fast, safely, and without restrictions. Plus, features like threat protection and ultra-fast speeds with Nord links mean you're not sacrificing performance for security. You get both. Right now, you can grab our special Space Nuts deal and get 4 months extra for free. Plus, there's a 30-day money-back guarantee, so it's completely risk-free to try. Just head along to our special URL, nordvpn.com/spacenuts. That's nordvpn.com/spacenuts, and don't forget to use the code SpaceNuts. That's nordvpn.com/spacenuts. Stay safe, stay private with NordVPN, our sponsor.
0G, and I feel fine.
Space Nuts.
Okay, Fred, our next story comes from Pete, who says, "Hi, great show, well done." Oh, thank you. In trying to understand the impact of dark matter on the stability of the galaxy, I was perplexed by the lack of reported impact on our solar system, and then closer to home, the Earth, the Moon, and space traffic. That led me to a realization that whilst we see visual images of galaxies that look full, that in reality, if all the baryonic matter in the galaxy was accumulated together, it would represent a minuscule percentage of the volume of the galaxy. That the galaxy may have 100 billion stars, but is basically empty. Dark matter, whatever it turns out to be, is likewise so sparsely distributed that it is undetectable at the solar system level. Maybe the professor could expand on these comments for the benefit of all of us who struggle to grasp the vastness of empty space that constitutes the galaxy and ultimately the universe. Many thanks from Pete. What do you reckon, Fred?
Well, Pete's right as well. We've done really well today. We've had 3 speculations, all of which have turned out to be on the money. It's the fact that dark matter, whilst we know it clumps on scales that are much bigger than the galaxy. So our galaxy is in a blob of dark matter that actually is much, much bigger than the galaxy itself. So what that means is that, exactly as Pete says, you've got to all intents and purposes, within the solar system, and actually within the galaxy itself too, you've got the kind of uniform background of dark matter whose gravitational influence is there, but is kind of acts equally in all directions to stuff that's immersed in it, if I can put it that way. So yes, the solar system's full of dark matter, but it's effectively uniform. It's just like a background uniformity, which is why when we calculate the orbits of planets and things like that, we can completely ignore it, because it's essentially a flat space of uniform gravitational influence, if I can put it that way. I don't think I'm explaining that very well, but that's the bottom line. And it's basically it's exactly what Pete said.
And what did he say?
He said what I've just said. That the blob of dark matter that the galaxy's in is effectively uniform on distances comparable with the solar system, and in fact on distances comparable with the stars in the galaxy as well.
Yeah, it seems to be a need of dark matter to have stuff to hang around.
Yes, we think it's the other way around. We think that the stuff gravitated inwards, being pulled
because
by
of
the dark matter. That's right, and that's what caused galaxies to form, sort of built on a scaffolding of dark matter, which was what was created in the Big Bang.
Right. Wow. Okay. That just makes it even more mysterious, really. Doesn't it?
Well, it neatly explains why galaxies are there, because
it's very convenient.
It is convenient to have galaxies. Yeah, this sort of web-like structure, which we think dark matter, that was the shape of dark matter. It was like a honeycomb of material, except it's not material as we know it. That web-like structure is actually a direct consequence of the Big Bang. It's what we expect. It's what we expect the Big Bang to do. And Geordie agrees with that.
Yes, he does.
Have noticed. Yeah, he's upset because.
Yeah, he's dealing with a dark matter by the sound of it. Poor old Geordie.
Geordie, it's all right. It's okay. Mate.
It's okay.
Yeah, his tail's gone up again. It was very down a second ago.
Yeah, we were talking about dark matter, and that's
what he is.
Yes,
very dark indeed. He's probably the blackest thing in the whole house. Yes.
I know there's we get so many questions about dark matter and dark energy and black holes. It's they're probably the top three things that people ask us about.
I think,
and Geordie, we ask about Geordie all the time. So, but
yeah,
it just never ceases to amaze me that like how long ago didn't we even know about dark matter, and now we've started thinking, well, okay, it's doing a lot more than we ever anticipated, and now we seem to have a total reliance on it to keep everything together. It's the glue of the universe.
Yep. It's a good way to put it.
Yeah. What? Write a book?
Radio. Should be on radio.
Oh right, yes. Maybe one day. But you think they'll ever crack it? I've probably asked that question many times, but do you think they'll ever figure out what this is and how it all came to be?
Yeah, I think so. And, there's ideas buzzing around all the time. We talked not very long ago about the idea that suddenly people are suspecting that that primordial black holes might be a reality. And they can come in any size you like rather than have to be bigger than the size of the sun. And so one that's smaller than the sun has been found. And that suggests that primordial black holes may exist. And that might open the whole debate again about whether dark matter is made of machos or WIMPs, with the machos being massive compact halo objects, that's things like black holes, and the WIMPs are weakly interacting massive particles, which is kind of the preferred view now. And then on top of that, there's the possibility that we've got it all wrong anyway, that it might be actually modified Newtonian dynamics that's at work. So it's still some open questions with regard to dark matter. And, we've been thinking about this seriously for almost the last 50 years. It was 1978 when Vera Rubin's observations really hit home that there was something very basic about the universe that we didn't understand.
Like how wasn't it throwing itself to pieces?
Yes, that's right.
That was the question.
Actually, that question was asked by Ken Freeman, who's an Australian astronomer. He published a paper in 1970, which was saying galaxies are rotating too fast to stay together.
Yeah.
Vera postulated that there are halos of stuff that keep them together, and that's when the whole dark matter vogue, if I can put it that way, started.
Yeah, and it's still the big question, isn't it?
It is.
One of several, but one of the biggest ones. Thank you, Pete. Great question, and thanks for sending it in.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem. We've had a main beam plus undervolt. Roger, main beam undervolt. Okay, stand by, 13. We're looking at it.
Space Nuts.
Our final question comes from, you were saying, Fred, that we've been right on the money. These questions have been, spot on until now.
Hello, Space Nuts! Martin Berman Gorvine here, writer extraordinaire in many genres, here to accept Professor Watson's thanks for the Bee Gees quip. And I'm asking today about another Bee Gee brother. This one may not even exist, and I know that nonetheless you have gotten questions about him before, And that would be Peel give. Yes, Peel give, otherwise known as the Big Leap. Can you somehow circumvent the absolute speed limit of the speed of light in the universe by having a quick dodge out into another universe where the speed of light is arbitrarily high, which is a staple of science fiction? Is this theoretically possible? And even if it were, would it be possible to go have a visit with Mr. Peel Gibb without being spaghettified and turned into mush of particles without even marinara sauce? Can't wait for the answer. Berman Gorvine, over and out, 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 out.
Thank you, Martin. I think he just brought our podcast episode back to kind of the average sphere in terms of... No, I'm kidding. Love you, Martin. Love you very much. Peel Gibb, the Big Leap. So I think, I'm scratching my head here. I think he's asking, is the absolute speed limit of light constant if you could go and visit another universe in comparison? Is that what he meant?
That's the bottom line of his question, yeah.
There's a one-word answer for this, and it could be one or the other.
Well, it is. It's no. But, just thinking aloud on that. So, first of all, it is possible that if there were other universes, some of the fundamental physical constants might be different. The charge on the electron might be different. The speed of light might be different. That's something we know so little about other universes, mainly because we don't know whether they exist, and there isn't really any theoretical framework that says they do. They have been suggested by some very eminent people, but we really don't have any more than suggestions. People have looked for evidence for other universes in the cosmic microwave background radiation that we were talking about a few minutes ago. But unless you have an eye of faith, which one or two people do, there's not really anything there, nothing to see there. So other universes may well not exist, and even if they do, they might end up having the same speed of light. We simply do not know. But I think the main problem is going to be getting from ours into another one, because the word universe means everything we can see and observe or deal with, transferring from this universe into another one, I suspect, is one that would, even with the most open-minded science fiction brain in the world, might cause problems. Unless you're Martin will cheerfully write about it, and I hope it's a bestseller.
I don't doubt it. I've read a bit of Martin's work and I've thoroughly enjoyed it. So, I would encourage to look up his books. There's a few goodies there. The speed of light intrigues me because we know what it is. We know how fast it is, 300,000 kilometres per second or whatever. And we can't even think about going near that speed. I mean, we can't even achieve 2% of the relativistic speed, and if we could, that'd be a major achievement. But it's an unfathomable number in the scheme of things, Fred.
It is, and the very good reasons for believing that nothing can go faster than that, and that's because as you accelerate things, any object with mass, as you accelerate it, the more energy it takes. So every meter per second that you add to its velocity, you kind of have huge energy penalties, and eventually, it all sort of basically asymptotes to infinity. In other words, you'd have to put infinite energy into something to accelerate something to the speed of light, and we haven't got infinite energy, so we're never going to do it. There'll be other problems as well. So it is a real speed limit. It's very sad from the point of view of science fiction writers or from scientists. You've got to find a way of getting around it. I think you're a dab hand at that. So, but that's what
I can't reveal anything. I'm just in the last couple of chapters of my trilogy, and I'm not going to blow the whistle on myself. No,
don't do that. Don't do that.
But yeah, short answer is yes. I've solved that.
Yeah, good. All right. Well, I'm glad you have. Let us know what you did to overcome this infinite energy requirement.
Yeah. There are ways, in theory, but
yes,
we haven't figured them out yet. So did we answer the question? Oh, yeah, it was no.
Yes, it's no.
It's no. Yes, it's no. Martin, no. But nice.
But I do like the idea. I do like the idea of the peel gib.
The peel gib, yes.
Yeah,
yes.
That's good.
Very interesting. Oh, Martin. If you've got questions for us, please go to our website and send them in. spacenutspodcast.com, spacenut's.io are our two URLs. We're working on a third URL. It's peelgib.com. No, probably not. But yeah, you can click on the AMA tab to send us questions. Don't forget to tell us who you are or where you're from. You can do that in audio or text format and have a look around while you're there. Don't forget to, if you will, to leave reviews on whatever podcasting platform you listen to us through or via or on. Reviews are very, very helpful. Apparently they tell people things about us that we might not want them to know. But anyway, if you would do us that kindness, we would be most appreciative. And we are done, Fred. Thank you very much. And you're off for a few weeks because you've got some travelling to do and some people to see and some bills to pay and all that kind of stuff.
Yeah, it's the travel that's taking me away. But I'm delighted that you will be able to keep the flag waving and keep the show on the road with our good friend John T. Horner.
Yes, John T. will be joining us from the University of Southern Queensland for a few weeks. Fred, thank you so much. Happy trails, and to you and Marnie, have a good trip, and we'll see you when you get back.
Sounds great. Many thanks, Andrew, and talk to you soon.
Indeed. Professor Fred Watson, astronomer at large, part of the team here at Space Nuts. And thanks to Hugh in the studio, who couldn't be with us today. He tried to peel a gib and nearly cut his finger off. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.